So first thing about stoichiometry is we got to work on balancing chemical equations, which most of you guys are probably familiar with, but we're going to do a couple problems to refresh your memories. Balancing equations is basically our way of making sure that when we have a chemical reaction like this, that both sides have equal amounts of elements. So the law, they might ask you questions about this, but this is called the law of conservation. My goodness, it's a long word. Conservation of matter. Okay, basically, you can't make matter out of nothing, and you can't get rid of matter completely. That's pretty much what the law says. So if I have 4 hydrogens on this side, then that means I have to have 4 hydrogens at the end of the reaction. And if I have 2 oxygens, I need to have 2 oxygens at the end of the reaction. That's the reason why we balance equations. It's because matter is conserved. You can't destroy or create matter. Okay, so that's why we balance. Couple terminology things. Things on the left side of the equation are starting ingredients, if you will. These are called reactants. And the compounds on the right side of the arrow, these are called products. So I'm going to use those terms just pretty loosely, just because it's part of the vernacular of chemistry. So just be aware of that. The chemicals you start with are reactants. The chemicals that you're making are products. Okay, but a lot of this probably is review for you guys if you took chem in the past. But any questions on the terminology?
No.
Okay. Just a quick thing about this. Don't kill yourself to memorize this. You might get a question or two here and there on practice problems or the AP test even, but it's not going to make or break your grade. So if you don't remember this, no stress about it. Okay. It's just the reasoning behind balancing. Okay, so we're going to skip all this. It's just more information about it. But let's see if you guys remember how to balance. If you remember how to balance, you can just kind of zone me out and just try 3.1 on your own. But if it's been a while, no worries. I'm going to go over 3.1 together. And then I'll have you guys try 3.2 on your own. Okay, so when you're balancing, the first thing you want to do is you want to identify all the elements that are in the equation. Easiest way to figure that out is just look at the capital letters. Capital N, so that's Na, sodium, capital H, and capital O. Okay, so these are the 3 elements that are present in the equation. And if you notice, you got the same thing on the right side of the arrow. Okay. All right, so first thing you want to do is you want to basically count how many of each element you have on the left and the right side of the arrow. So I like to make a quick little table. If you have a different method of doing it, totally fine. You don't have to do it my way. I'm just showing you the way that makes sense for my brain. But if you take a look at the left side of the arrow, the reactant side, you got 1 sodium, 2 hydrogens, and 1 oxygen. And on the product side, you have 1 sodium, 1 oxygen, and 3 hydrogens. Okay, so that's how you can count or take account of how many of each element you have on the left and the right side. All right, now we want to balance, which means we have to have the same number of each element on both sides of the arrow. So if you take a look, our problem right now is going to be hydrogen. Okay, we have more hydrogen on the product side than the reactant side. So the trick is you always want to add to the side that has fewer first. So there are fewer hydrogens on the reactant side, so we got to add hydrogen. But we can't just add a hydrogen by itself, because if you do that, you're changing the reaction. You have to add what's already there. So the molecule that has hydrogen is H2O, so we have to add another H2O molecule, which will change our numbers. Okay, if you add another H2O, now there are 4 hydrogens on the left side and 2 oxygens on the left side. And then to balance it on the right side, you're going to notice that our hydrogen is still messed up, and now our oxygen is messed up as well. So now we have an option, right? Because we could add another H2 here, but if we do that, we're kind of making the problem worse, right? Because you're messing up hydrogen again, but you're not fixing the other problem. So we're probably going to have to add NaOH. So we're going to add NaOH. That's going to change our numbers on the right side. Now we got 2 sodiums. You added a hydrogen, so that's 4. You added an oxygen, so that's 2. And then you can probably see how to fix it up at the very end. You need another sodium on the left side, which balances out all the elements. Okay. Alright, so to finish up, we have to add numbers in front of the molecules that we have multiple of. So we got 2 Na, so we're going to put a 2 right here. We got 2 water, so we put a 2 right here. And then 2 NaOHs, so we put a 2 in the front. Okay, and we didn't add any H2s, so we can just leave that blank. Alright, so the final balanced equation, I'll just box it up what it should look like. The formatting should look something like this. Okay, if you guys notice, we didn't add any new chemicals to it. All we did was add numbers in the front of the formulas. These numbers are called coefficients. Okay, so if you see that term, that's what it means. It's just the number of molecules you have in that equation. But that's how you balance.
Why does he record everything on his notes? Like he's texting his mom.
What's wrong with yours? Oh, I never paused that. Alrighty guys, so I got the answer up on the screen for you. Your coefficient should be 2623. You got something like that? Great job. If not, I'll be honest, this is kind of a harder balancing, a lot more movement. I'll go through it real quick how to get this. So we got aluminum, we got hydrogen, and we got chlorine. Left side we got 1, 1, and 1. And then on the right side we have 1, 3, and 2. Okay. So first thing you're going to notice is that the hydrogen and the chlorines are not balanced. So if we add another one right here, that's going to change our numbers to 2 and 2. Okay, but then you're going to notice that you see how chlorine goes up by 1 and then on the left side, but it needs to go up by 3 on this side, right? And so if we add another HCl right here, that's going to get us to 3 and 3. So it looks like the chlorines are good, but the hydrogen is messed up. So we got to add, exactly, you add another hydrogen, that gets us to 4. But then the hydrogens are messed up again. So you kind of just keep adding to the side that has less. Eventually, you're going to get to the point where you're going to need the coefficients that we talked about. You're going to need 6 of these. You're going to end up with 3, and then 2, and then 2. Okay, but that's kind of the way that you want to balance. You just want to keep adding the one that you have less of, and that'll get you to your coefficients. If your numbers get too large, though, just a heads up, like if you're getting into like double digits, you probably miscounted something. For this class and for the AP test, they're not going to give you any like ridiculous balancing ones. So once you start hitting double digits for your coefficients, you probably messed up somewhere in terms of the counting. Alright, so the next thing we're going to talk about is pretty simple. It's something called percent composition, and it's exactly what it sounds like. It's basically what percentage of a molecule comes from a certain element. Okay, so easiest way to do this, I think, is with a problem. So what we're going to do is we're going to find the percent composition by mass of CO2. Okay, so we're going to look at CO2. And you'll need a periodic table for this, so you can take yours out right now. Or you could share with somebody, pull it up on your Chromebook, whatnot. And what we're going to do is we're going to find the percentage of CO2, the mass that comes from carbon and oxygen. So if you take a look at CO2, the first thing you want to do is you want to find the total weight of this substance. So we're going to look at CO2. If you look at carbon on the periodic table, it's 12. And oxygen is 16. Okay, so 2 oxygen. So that means that CO2 has a total mass of 44. Okay, so quick thing about the 0.1. I know carbon is 0.01. However, you can just drop it. It's never going to make a difference. Okay, it's negligible enough. And we use carbon so much, you can just always do 12. Okay, same thing with hydrogen. You can always use 1. Nitrogen, always use 14, so on and so forth. If it's like really close, like 0.01, you can drop to 0.01. It's going to be a negligible difference in your answers. So a little quick trick for you so that you don't put more clicks on your calculator. Okay, so CO2 has a total mass of 44 AMU. All right, so the question's asking to find the percentage by mass of both carbon and oxygen. I'll do carbon with you guys just to show you the formula, and then you guys can try oxygen on your own. So the way that you find the percentage by mass of something is carbon has a mass of 12 AMU, right? And so you just take carbon's mass, so 12 AMU, divided by the total mass, which is 44 AMU, and then we just multiply that by 100%. Quick note, don't punch in the percent sign on your calculator. That'll divide it by 100 again. You can just add the percentage sign at the very end like a unit of measurement. Okay. So this one's pretty easy, 12 divided by 44, and that's going to give you about 27.27%. All right, any questions on percent comp? Yeah, hopefully pretty easy. If you guys have done percentages in math or just kind of in your own lives, it's the same formula. Whatever you're looking at, divided by the total times 100. All right, so take about a minute and a half. See if you guys can do the percent of CO2 that oxygen makes up, and then we'll go over it, and then we'll move on. All right, guys, let's go over the oxygen portion. Oh, and then, sorry, I forgot I should have labeled this. This is going to be a carbon. And then for oxygen, for this one, oxygen is 16, but you notice how there's 2 of them in CO2, right? And so we got to put 32 as the weight of oxygen, divided by 44, and then times 100%. Okay, so that's one way you can do it, just using the standard percent comp formula. There's actually a faster way to do it, though. If you notice, CO2 is made out of carbon and oxygen, right? If you found carbon, you can just subtract it from 100%, and that'll give you pretty much the same answer. Okay, so something around 72.73%. Now, just a quick heads up, as we go more into chemistry, you guys probably have noticed this in your other chem classes and math classes, your answers will not be exactly the same as mine. That's totally fine. As long as it's very similar, it's close, then you're good. If you got like 72.7 whatever, you're good. All right, any questions on 3.3? Okay, let's have you guys try 3.4 on your own. You can work with the person next to you. If you want to split it up, you can as well. Okay, so moving on from percent comp to this concept called the chemical mole. You guys have probably heard of this term in your previous chem classes. It's not that ugly animal that lives in the ground, okay? A mole, sometimes they write it just as M-O-L, so if you ever see M-O-L, that works as that's another way of saying it. But if you have a mole of something, it's a way of counting. So just like how we say a dozen of something is 12, right? A pair of something is 2. A mole of something is when you have this much of something, okay? And what this exponent means is basically you move the decimal 23 times to the right. So very, very big number, okay? The reason why we use moles to count atoms and molecules and whatnot is because obviously they're so small, you can't count them like 100 at a time or 1,000 at a time. We need to count them a mole at a time. Now, as we talk about that, let's take a look at the periodic table real quick. We've been talking about the number at the bottom of the box, and we said that this is AMU, right? Okay, but we can also talk about this in terms of something called molar mass. Okay, so this number is fun because not only does it tell you the AMU, it also tells you how many grams 1 mole of that element weighs. So when you have 6.023 times 10 to the 23rd of hydrogen, that means it's going to weigh 1.01 grams. Okay, so the unit of measurement that's down here is AMU, but it could also be grams per mole. Okay, so that's how many grams 1 mole of that element weighs. So if you have a mole of hydrogen, it's going to weigh 1.01 grams. If you have a mole of lithium, it's going to weigh 6.94 grams, so on and so forth. Okay, so that's another way that we can use this number at the bottom of the box on the periodic table. All right, so using that, we can start doing conversions with when we're talking about different elements and molecules. So let's start right here. It's asking how many iron atoms are in 1.12 moles of iron. So we got to do some dimensional analysis, which you should have looked at in your Unit 1, which everyone read already, right? Yes, okay. And one person that didn't. Okay, so we got 1.12 moles of iron. So we're going to start dimensional analysis by writing down our starting number, which is 1.12 moles of iron. And we want to convert this value into, looks like, atoms. And so we got to set up a fraction. Okay, now to get rid of moles, right, if you have something on the top of a fraction, you need the same thing on the bottom of the fraction. So we're going to put moles of iron on the bottom. And then we want to find atoms. So we're going to put atoms on the top. Now, in order to get the values of this fraction, we need to find some type of conversion factor, right, which is right here. Okay, because a mole is equal to this many of something. So moles is on the bottom of the fraction. We've got a 1 in front of moles for the conversion factor, so we put a 1 on the bottom. And then on the top, we're going to put 6.022 times 10 to the 23rd. Okay, and that's how you would do the conversion. All right, now, if you are blessed enough to have a calculator that can do these scientific notation equations, then great, you can just punch that in directly. But if you don't, or you're using your phone calculator just because we're not taking a test, I'm going to show you guys how to do this calculation without one of those fancy calculators, okay? So we can ignore the 1 on the bottom because if you divide by 1, it's the same number, right? So the way that you solve this is you're just going to do what's on the equation. So you got the numbers on the top of the fraction. So what it's going to look like is we're doing 1.12 times, and then it'll be 6.022 times 10 to the 23rd. So this is the actual operation that we're doing. Sorry, let me fix my 2 right there. All right, now the way that you want to solve this out is very simple. You first take a look at the normal numbers. Okay, that exponent thing is weird, so we're going to ignore that for now. And what you're going to do is you're going to take the normal numbers and do the operation that it tells you to do. It's multiplying, right? So what we're going to do is we're just going to multiply the 2 normal numbers. So 1.12 times 6.022. And so we'll get this value right here. So 6.74. And then what we do is we take this exponent and then we just add it right behind it, times 10 to the 23rd. And there you go. That's going to be our answer. So I know the scientific notation looks a little bit intimidating, but even if you don't have one of those fancy calculators, pretty easy to do. Just take the normal numbers, do the operation, and add the times 10 to the whatever behind it. Okay. There will be some situations where you got to move the decimal. I'll talk about that in future examples, but that's pretty much the basic gist of it. All right, let's try 3.6 together now. If you feel comfortable doing this, by the way, at any point, you can just kind of ignore me and solve the problem and just check your answers afterwards. But I like to go over step by step just in case there are people who still need a little bit extra help. But feel free to solve the problem on your own if you feel confident to try it out. All right, so this problem says you got a beaker containing 4 moles of magnesium nitrate, which you guys know how to name now, right? Yes, you do. Okay. So you got 4 moles of MgNO32, and you want to convert this into how many individual NO3 minus ions are there. So the first thing that you want to do is you want to turn this from moles into the molecules. Okay, so we're going to take this and we're going to set up a conversion factor. We want to get rid of moles of magnesium nitrate, so we're going to put that on the bottom. And first thing we want to do is we want to turn it into just molecules. Okay, so we want to turn moles into individual molecules of MgNO32. Okay, and let me give you 30 seconds to see if you can plug in the correct numbers on this fraction using our conversion factor. Okay, see if you guys can put the correct number or the numbers in the correct position. Alright, so if you guys notice, it's the same thing as the one up here. You got moles on the bottom, so it's 1 mole, so we put a 1 on the bottom. And then the conversion is 6.022 times 10 to the 23rd, so we put that on the top. 6.022 times 10 to the 23rd. Alright, now we are not done yet, because if you notice, the question is not asking about magnesium nitrate, right? It's asking us how many individual nitrates are there. So we can't stop here. We actually need to add one more conversion factor. And what we have to do is we need to turn MgNO32, and we need to turn that into nitrate, NO3 minus. Alright, so in order to get these numbers, we actually don't have like a conversion factor, but we can find it using the actual chemical formula. If you take a look at magnesium nitrates, how many nitrates are inside of one magnesium nitrate? 2, right? Because there's a parentheses around nitrate and there's a 2, which means that we have 2 nitrates in every one magnesium nitrate. So that's the final conversion factor in order to get our final answer. Okay, so that's kind of the trick for that problem. And the AP test actually does have problems like this where they'll give you an ionic compound, and then they'll ask you, hey, how many of this ion is inside of it? So just be very careful when you're looking at these problems to make sure that you're solving for exactly what the problem is asking for. Okay, so let's solve the math now. So again, to do the math, we want to take the normal numbers and then add the exponent at the end. So our normal number is 4 times 6.022 and then times 2. And so our normal numbers are going to give us, sorry, I'm going to write it up here, 48.176, and then we just add the scientific notation after it. So times 10 to the 23rd. Okay, so this is going to be our answer. Incomplete answer. Okay. And again, all we did was we took the normal numbers 4, 6.022, and 2, and we multiplied them, and then we got 10 times 10 to the 23rd. Yeah, what's up? Correct, yeah. Yeah, so if you guys remember from Unit 1, in order to have actual scientific notation, you can only have one number in front of the decimal. So the problem here, if you guys notice, it's 2 numbers, right? So what we have to do is we need to move the decimal 1 time to the left. And so this is going to turn to 4.8176. And if you move the decimal to the left, okay, your exponent is going to go up. Okay, so this will become times 10 to the 24 because you moved it 1 time to the left. If you moved it 2 times to the left, it would be 25, 3 times 26, so on and so forth. If you moved it to the right, then that means the number would go down. Okay, so if you want to make a note of that, you guys can. If you move the number to the left, or sorry, the decimal to the left, the exponent goes up. If you move it to the right, it's going to go down. And then the units of measurement is still going to be the same. So NO3 minus ions. Okay, so just make sure you're comfortable with scientific notation. Once we get to the actual meat of AP Chem, especially second semester, we'll be doing a lot of scientific notation thing. Okay, so if you need extra practice, I would love to give you extra practice problems, but just make sure that you're comfortable doing things like this, just moving the decimal, so on and so forth. Okay, so 3.7. Okay, so let's say that you have a balloon and it contains 3.5 grams of CO2 gas. So our starting number here is 3.5 grams of CO2. Okay, and what you want to do is you want to convert this from grams into molecules. Okay, so the way that you would do this is you got to use your periodic table now. Because you can't go straight from grams to molecules. In order to go to molecules, you need moles, right? And so what you got to do is you got to set up a fraction where first you turn grams into moles, and then you need a second fraction where you turn your moles into molecules. Okay, so this is kind of the main skill of dimensional analysis. It's figuring out how to get from one unit of measurement to another unit of measurement. How many different fractions or conversion factors you need in order to go to a different unit of measurement. All right, now I'm going to have you guys try solving this on your own. This first conversion factor, if you notice, is grams and moles, right? So this unit of measurement comes from the molar mass. So you're going to go on the periodic table or from the previous problem that we just did earlier in this lecture to find the molar mass of CO2. And then here, you're going to use this conversion factor right here. And then you're going to try to solve. So let me give you guys about 2 minutes to try this out. Check with your partner if you guys finish early. We'll go over it, and then we'll have you try another one on your own, and then we'll move on. Okay, guys, so we are going to plug in our numbers now. So let's start with the molar mass. You guys could have done this on the periodic table, but if you looked at the first problem we did, first or second problem we did, we saw that CO2 is 44 AMU, right? And then we just said that AMU is pretty much the same thing as grams per mole. So 44 grams per means in one, right? So in 1 mole. So 44 grams goes on the bottom, and 1 mole goes on top. And then for this fraction, we put the 6.022 times 10 to the 20. Oh, I put 3. My bad. 23 on the top. I know. And then 1 on the bottom. And so our operation is right here. 3.5 divided by 44, because it's on the bottom, times 6.022 times 10 to the 23rd. So here we do the same thing. We take the normal numbers and do the operation. So 3.5 divided by 44, and then you multiply that by 6.022 times 10 to the 23rd. Or sorry, just 6.022. That should give you 0.479. And then if you guys notice, the decimal is in front of the number, so we got to move it to the right 1 time. And if we do that, we got to drop the exponent 1 value to 22. And so that's going to be our final answer. Okay. Alrighty, guys. So I got pretty much most of the answer up there. I realized I forgot to tell you guys how to do the final exponent part if you have multiple of the scientific notation, but it's really easy. I'll go over in a second. So the setup should be your starting number, which is 4.12 times 10 to the 24. You want to turn atoms to moles before you could turn it into grams. So that's why you have moles, atoms, grams, moles. So first fraction, you want to get rid of atoms, so you put the big number on the bottom, 1 on the top, and then the molar mass of iron from the periodic table for this third fraction. Okay, I put the operation here for you so you can look at it, but you're going to take this number divided by this number times 55.84, and if you do all the normal numbers, you'll end up with 38.2. Everybody good that part? Okay, now if you notice, we still have the times 10 to the whatever, right, left over. Okay, now if you remember from your algebra rules, if you have two numbers where you have the same base but different exponents and you are dividing it, all you got to do is you subtract the exponents. So 24 minus 23, that is going to leave you with 38.2 times 10 to the power of 1, which is 10. And so your answer here is going to be 382 grams. Okay, and that's about as tough as these dimensional analysis in terms of like straight up converting from atoms to grams and whatnot are going to be. So if you guys got that on your own, you're in great shape. That's about as tough as these types of problems you're going to get. Okay, so we talked about empirical formulas very briefly last class, right? This is the one where we're talking about ratios. So for example, H2O2 hydrogen peroxide, the molecular formula, if you guys remember, and you guys don't need to write this down. We already did this last class. This is the same example too. The molecular formula of hydrogen peroxide is H2O2 because it's made out of 2 hydrogens, 2 oxygens. But the empirical formula, if you guys remember, is the formula that gives you the ratio. The ratio is 1 to 1. So the empirical formula for hydrogen peroxide will be HO. Okay? Remember this last class?
Yeah.
Okay. All right, so today, like I promised, we'll talk about why we use empirical formulas. There's a lot of writing here, and this thing that you don't, if you want to read it, you can. But we're going to jump into a problem, and I'm going to show you guys how to use empirical formulas. So the reason why we use empirical formulas is because sometimes we are studying something, and we don't know the exact chemical formula yet. However, we can use different techniques to find the percentages of each element inside of that compound or whatever we're studying. And so that's where empirical formulas come in. So 3.9, it says, determine the empirical formula of a compound that is 81.32% carbon, 5.12% hydrogen, and 13.56% oxygen. Okay, so we have some unknown chemical. We know the percentages of each element, and we got to figure out the ratios to get the empirical formula. So the way that you solve this problem, the easiest way is first, you're going to assume that you have a 100-gram sample. Okay, why 100 grams? Because if you have 100 grams of something and you have the percentages, it just makes the numbers really easy to work with. Okay, so if you have a 100-gram sample of this compound, how many grams is carbon?
81.
Yeah, it's just the percentage, right? So it'll be 81.32 grams of carbon in this 100-gram sample. There will be 5.12 grams of hydrogen. And there will be 13.56 grams, ooh, that's an ugly 6, of oxygen. Okay, so CHO. Okay, so the first thing you want to do after you, I guess the second thing you want to do is once you have your 100-gram sample and the percentages, you want to convert all of these into moles. Okay, so I'll do the first one with you just to kind of give you an idea. You're going to take carbon. Carbon is 12 grams per 1 mole, and you can get this from the periodic table. And then once you convert this, that will give you your moles of carbon inside of that sample. So what you're doing is turning your grams of that element into moles. So let me give you about a minute 30. See if you guys can convert all 3 of these into moles of the respective element. Okay, use your periodic table to get the molar masses. I do recommend writing more decimals for these empiricals, and I'll show you guys why in a second. So instead of 8.4, see if you guys can write 8.45, so on and so forth. For these, you want to get a little bit more because it'll make your numbers actually a little bit easier to work with once we do the next step of these types of problems. Okay, so maybe about 4, maybe 5, depending on what the problem is. This one, obviously, you can't do more because it's just 5.12, but just a heads up for empiricals, adding a couple more decimals will probably help you out in the long run. Okay, so once you have your grams converted into moles, what we're going to do is you want to basically use this as kind of a starting point for your chemical formula. So we're going to write a chemical formula. This compound is made out of C, and there are about 7766 moles. So I know that usually we have a whole number for the subscript, but we're going to do this for now. We're going to do H 5.12 and then O 0.8475. Okay, because what this calculation, this conversion from grams to moles shows us is the ratio of moles between all of the between the elements in this compound. And then what you want to do to simplify this is you want to divide by the smallest number. Okay, so you want to identify what the smallest number is, and then you want to divide all of the values by that number. So if you take a look, smallest number is 0.8475. So we're going to divide all of these numbers by 0.8475. So we're going to take the carbon. The carbon has 6.7766. We're going to divide that by 0.8475. And if you notice, what whole number is this really close to? 8, right? So we can, this is going to be about C8. H is 5.12. We divide it by the smallest number, 0.8475. What whole number is this really close to? 6. So H is going to get you to 6. And obviously, this value divided by itself is 1. And so this is going to be the empirical formula of your compound. Okay, so we get the ratios between the elements inside of this compound. Okay. We're going to do another practice one just to make sure we lock this skill in. Just heads up, this will 100% be on your exam. You have a very high chance of having it on the AP test. AP test loves asking empirical formula questions. So just make sure that you're very comfortable determining empirical formulas when they give you the mass percentages. Okay, so the first couple steps were pretty much, or actually the majority of the question was pretty much the same. You're going to take your percentages, assume a 100-gram sample, and convert to moles. Everybody good with that, right? It's pretty much what we did. And then you'll identify that the smaller number is 3.41. So if you notice, these two are pretty much the same value. So that gives you 1 for the C, 1 for the O. The problem, I'll see it. And then the problem is that for H, you get 1.344, right? But if you remember, this is not close to a whole number, right? So we can't round down or round up here. And so the trick to figuring out this problem is we need to just kind of multiply to see if we can get it closer. So if you guys know, 0.3 is about the same as 1/3, right? And if you multiply that by 3, that gets you to about 0.9, right? And that's close enough for us to round. So the last step here is you want to do times 3, and so your empirical formula will be C3H. Whoa, I just blanked out. 0.3. 4. Oh, whoa, sorry, I started brain fart. Okay, 1.3 times 3 is 3.9, which is about 4. Yes. Oh, and then O3. Thank you. Sorry, guys. It's Friday. I'm out of it, too. Literally on the last question, I slipped up. Okay, so C3H4O3 because you multiply it by 3. So if you get a number where the decimal is very, like, in the middle, try multiplying it by some whole numbers to see if you can get it close to a point where you can round.